There is a place in our universe where time itself comes to a stop, where the laws of physics, the rules that govern every star, every planet, every atom in your body, break down and fail. It has no surface, no solid ground. It is a hole in the fabric of reality, and anything that crosses its edge, matter, light, information itself, leaves this universe forever. If you fell in, you would not feel a wall or a barrier. You would cross the point of no return without noticing, and by the time you understood, escape would not just be difficult, it would be as impossible as traveling backward in time. To turn our entire planet into one of these objects, you would have to crush the Earth, every mountain, every ocean, all of it, into a sphere the size of a marble. The universe has made them in staggering numbers, an estimated 100 million in our galaxy alone. Some are the corpses of dead stars, some are monsters as heavy as 66 billion suns, and one of them sits at the center of everything you have ever seen. This is the story of black holes, the objects science declared impossible, then found everywhere. The story begins not with a telescope, but with a thought experiment. In 1783, an English clergyman named John Mitchell asked a deceptively simple question: could a star grow so massive that its own light could not escape it? Mitchell called them dark stars, invisible by definition, detectable only by their pull on the things around them. His idea was 2 centuries early and almost exactly right. The mathematics that made dark stars real arrived in 1915, when Albert Einstein published his general theory of relativity, a new picture of gravity, not as a force, but as the bending of space and time itself by mass. And here the story takes a turn that sounds invented. The first exact solution to Einstein's equations was not worked out in a university office. It was worked out on the Russian front of the First World War. Karl Schwarzschild, a German astrophysicist serving as an artillery officer, did the calculation while at war. His solution described exactly how spacetime curves around a compact mass, and it contained something disturbing. Below a critical radius, the math didn't just bend space, it broke. At a certain distance from the center, time and space traded places, and nothing could move outward again. Schwarzschild mailed his papers to Einstein and was dead within months of an illness contracted at the front. He never learned what his wartime mathematics had uncovered. For decades, most physicists, including Einstein himself, refused to believe these objects could actually form. The mathematics allowed them, surely nature would not. They were wrong, and in 1967, the physicist John Wheeler gave the impossible objects the name that stuck: black holes. You cannot see a black hole, so how do you find one? The answer came from an entirely new kind of astronomy and a rocket. In 1964, a sounding rocket carrying X-ray detectors made a brief flight above the atmosphere and caught something burning in the constellation Cygnus. The source was named Cygnus X1, and it was one of the brightest X-ray objects in the sky. Something out there was heating gas to millions of degrees. When astronomers found the spot, they saw only a blue supergiant star. But the star was moving, swinging in a circle every 5.5 days, around a companion that could not be seen at all. The invisible companion was far heavier than any dead star should be. The supergiant was orbiting something dark, compact, and by current measurements, about 21 times the mass of our sun, and it was feeding it. Gas torn from the supergiant spirals inward, accelerating toward the speed of light, shrieking at millions of degrees in X-rays, a scream we can detect from 7,000 light-years away. That scream was the evidence. Stephen Hawking famously bet the physicist Kip Thorne that Cygnus X1 would turn out to be no black hole at all. He called the bet his insurance policy. In 1990, with the evidence overwhelming, Hawking gave in and conceded. The first black hole was real. So what would it actually be like to fall in? The physics has an answer, and it is stranger than any fiction. Fall toward a small black hole, one born from a dead star, and you would never even reach the edge in one piece. Gravity at your feet would outpull gravity at your head so violently that you would be stretched into a ribbon of atoms. Physicists call this, with a straight face, spaghettification. But fall toward a giant, a supermassive black hole, and the horizon is so vast that gravity changes gently across your body. You could cross the point of no return and feel nothing, no jolt, no warning, no sign. Someone watching from far away would see something very different. They would see you slow down as you approach the horizon. Your image would grow dimmer, redder, and freeze. To the outside universe, you never quite fall in. Time near the horizon runs that much slower. This is not an illusion. Gravity genuinely slows time. Clocks on Earth's surface tick slower than clocks on satellites. Your phone's GPS corrects for it every second. A black hole simply takes that everyday truth to its absolute limit. Close to the hole, light itself gets trapped in orbit, a ring of photons endlessly circling a sphere of perfect black. If you could stand there, you could look to your side and see the back of your own head. And past the horizon, everything falls toward the center, toward a place the equations call a singularity, where density becomes infinite and the mathematics of our universe stops making sense. Whatever truly happens there, no message about it can ever come back out. For most of the 20th century, black holes were thought to be rare freaks. Then we looked at the center of our own galaxy. 26,000 light-years away, in the heart of the Milky Way, whole stars are being whipped around a single invisible point, the fastest of them reaching nearly 3% of the speed of light. For decades, two teams of astronomers tracked those stars, orbit after orbit, year after year. Every measurement pointed to the same conclusion: more than 4 million suns worth of mass, crammed into a region smaller than our solar system, emitting almost nothing. It is called Sagittarius A star. It is the supermassive black hole at the center of our galaxy, and the work that proved it real won the 2020 Nobel Prize in Physics. Then astronomers did something no one thought possible. They photographed one. The Event Horizon Telescope linked radio dishes on 4 continents into a single virtual telescope, effectively the size of planet Earth, sharp enough to read a newspaper in New York from a sidewalk cafe in Paris. In April 2019, they released the first image in human history of a black hole, a ring of superheated gas around a shadow of nothing, in the galaxy M87, a black hole of 6.5 billion solar masses, 55 million light-years away. 3 years later, they did it again, this time at home. The glowing ring of Sagittarius A star, our own central black hole, photographed for the first time. The impossible object photographed twice. M87's giant does not just sit there. It launches a jet of plasma thousands of light-years long, moving at nearly the speed of light, a beam of matter fired across its own galaxy by raw gravity. And in the deep past of the universe, feeding black holes burned brighter than anything else in existence. We call them quasars, single objects outshining entire galaxies of hundreds of billions of stars. The heaviest of them defy belief. A quasar known as Ton 618 harbors one of the most massive black holes ever measured, roughly 66 billion times the mass of the Sun. Its event horizon is so large that our entire solar system, the Sun, every planet out past Neptune, would vanish into it like a pebble into the ocean. Light itself would need around 2 weeks just to cross it. They are not all far away. In 2022, astronomers found a quiet, sun-like star in the constellation Ophiuchus, wobbling around an invisible companion, the nearest black hole we know of, Gaia BH1, about 1,560 light-years from your front door. It isn't feeding, so it doesn't glow. It just waits in the dark, and statistically, millions upon millions more like it are drifting through our galaxy right now, unseen. On the 14th of September 2015, a signal reached Earth from a collision that happened before complex life existed on this planet. 1.3 billion years ago, in a distant galaxy, 2 black holes, one of 36 solar masses, one of 29, spiraled into each other at half the speed of light and merged. In the final fraction of a second, 3 entire suns' worth of mass was converted into pure energy, not as light, as gravitational waves, ripples in the fabric of space itself. For that brief instant, the collision's power output exceeded the light of every star in the observable universe, combined. The ripples crossed intergalactic space for over 1 billion years, and on that September morning they swept through the Earth, stretching and squeezing the entire planet by a fraction of the width of a single proton. 2 machines, laser rulers 4 kilometers long, in Louisiana and Washington state, felt it. A century after Einstein predicted gravitational waves, we heard 2 black holes collide. The discovery won the Nobel Prize 2 years later. Since then, detectors have caught black hole collisions by the hundreds. The universe, it turns out, is ringing like a bell. We simply never had ears until now. And yet the deepest mystery is not how black holes form or how big they grow. It is what they do to information and what happens when they die. In 1974, Stephen Hawking showed mathematically that black holes are not perfectly black. Quantum effects at the horizon make them leak, glowing, unimaginably faintly, and ever so slowly evaporating. Given enough time, every black hole in the universe will shrink, brighten, and vanish. For a black hole the mass of our sun, that funeral takes 10 to the power of 67 years, a 1 followed by 67 zeros. Our universe is 14 billion years old. The era of black holes has barely begun. But if a black hole evaporates completely, what happens to everything it ever swallowed? Quantum mechanics insists information can never be destroyed. Black holes appear to destroy it. One of those statements has to be wrong, and half a century later, physicists are still fighting about which one. And the mysteries are getting bigger. The James Webb Space Telescope is now finding enormous black holes shockingly early in cosmic history, million solar mass giants, fully formed when the universe was only a few 100 million years old. That may be too early for dead stars to have built them. Some astronomers now suspect the first black holes never came from stars at all, that vast clouds of primordial gas collapsed directly into black holes, skipping the star stage entirely. If that is true, then black holes are not just the destroyers at the end of a star's story. They may have been there at the beginning, the seeds around which the first galaxies, including ours, took shape. Which means the black hole at the center of the Milky Way may not merely live in our galaxy. Our galaxy may exist in part because of it. The object science refused to believe in turned out to be everywhere, sculpting galaxies, ringing spacetime, and holding open questions our best physics still cannot answer. Not bad for a hole. Next time we turn from the largest objects in the universe to two of the smallest ever to leave home. A pair of machines, built in the 1970s with less computing power than a car key, that are now the only human-made objects in interstellar space. They were designed to last 5 years. They are still calling home after nearly 50, their signal arriving at Earth 20 billion times fainter than the power of a watch battery. Voyager, the longest journey humanity has ever taken.